Hello everyone, my name is Hugo Bouteiller. I'm a third-year PhD student, and I'm very pleased to share with you a part of my PhD work. So this will be about the non-conventional synthesis and characterization of a doped rare earth antimonide for high-temperature thermoelectric applications. So if you're not familiar with thermoelectric materials, don't be afraid. I will briefly introduce the main concept of this field. So first, imagine that you have a bar, okay, and you apply a temperature difference between the top and the bottom of your bar. Then you will get a physical effect that we call the Seebeck effect. You will get a voltage difference between the top and the bottom of your bar, okay? So thanks to the temperature gradient, you can basically convert heat into electricity, and this is why we are mainly interested in developing high-performance thermoelectric materials. Okay, so how do we assess the performance of the thermoelectric materials? We use what we call the so-called figure of merit ZT that is shown here. Okay, so of course we want the Seebeck coefficient that is describing the Seebeck effect as high as possible. Okay. And of course, we need the bar to be conductive if we want to get an electrical current out of it. So we need a high electrical conductivity. But at the same time, we need a low thermal conductivity because we want to maintain the temperature difference between the top and the bottom as high as possible. So we need thermal conductivity very low. And the thermal conductivity can be described by two different terms, an electrical contribution and the lattice part of the thermal conductivity, okay? So one of the main problems in thermoelectrics is that all these properties are correlated, okay? So we need to control the charge carrier concentration, okay? If this charge carrier concentration is very high, you will get a high electrical conductivity. And at the same time, you will get a high thermal conductivity because the electrons or holes, depending on the case, will contribute much to both electrical and thermal conductivities. Okay, so we need to get a compromise between both, like, all of the terms that describe the figure of merit. Okay, and the highest Seebeck coefficients are obtained for very low carrier concentration at the same time. So basically, we need to focus on a very narrow range of carrier concentration that are, in general, obtained for semiconducting materials and highly doped semiconductors. Okay, and at the same time, we need to decrease the lattice part of the thermal conductivity here. That is the only term that is independent on the charge carrier concentration. Okay, and to do that, we can play with the crystalline structure, for example, to scatter the phonon as much as possible. So as a general concept, we need a material that is phonon glass-like, okay, that scatters the phonons as much as possible, and at the same time we need a crystalline material because we need a highway for electrons to get a sufficiently high electrical conductivity. So now let's get into the main work of this poster, okay? So I worked on a rare earth antimonide, which the structure is displayed here. So we have ytterbium-4 antimony-free formula, and the environment of both ytterbium and antimony atoms are really distorted. So we have significantly high complexity that allow the low thermal conductivity of this material. So our trip begins with a little bit of background description of the previous work that was done before my PhD started. So this work was conducted on the mother material at first. So this material displays a p-type conducting behavior. As you can see here, the Seebeck coefficient is mainly positive on the high temperature range. And if we count the charge of this material, we can see that ytterbium are giving electrons to the anionic framework here, and the antimony atoms are accepting 3 electrons each. And magnetic studies have shown that the oxidation state of ytterbium is mainly 2+, while we can have a mixed valency for this lanthonide. So basically that means that only 8 electrons are given by the ytterbium metals to the anionic antimonides. So that means that we have a p-type semiconducting behavior, and also what we want to do now is to improve the thermoelectric properties by lowering the hole concentration by introducing more electrons to the system, by introducing lanthanum, which is oxidation state +3 mainly. Okay. So by doing so, we add more electrons to the system and we reduce the hole concentration. And this is what was performed. And we can clearly see that the Seebeck coefficient is significantly improved by doping of lanthanum on the ytterbium site. And at the same time, the resistivity is quite close to the mother material. So this is very interesting for getting high-performance thermoelectric materials. Also, we can clearly see that the thermal conductivity is low enough to obtain high figure of merit. As you can see here, we have figure of merit that is above 0.7 at very high temperatures, above 1200 kelvins. So this is really interesting because this is a high performance thermoelectric material in this temperature range. So another investigation was conducting on the doping with bismuth on the antimony side this time. And as you can see here on the results that were obtained, we can clearly see that the Seebeck coefficient is improved, as well as the resistivity is decreased by the introduction of bismuth into the structure. So this is quite unexpected, as if the Seebeck coefficient is improved, we can expect a higher resistivity, but actually we have kind of a synergical effect for this composition. So this is really great for having good thermoelectric properties. And starting from this point, I investigating the doping on both sides, both ytterbium side by introducing lanthanum and doping also on the antimony side to get even higher doping on both sides and try to improve the thermoelectric properties even higher with that doping. So first, I started with some experimental work where I did all my synthesis in niobium tubes, as you can see here. So these tubes were done thanks to a homemade apparatus that allowed me to melt the niobium on the edges, and thanks to this we can do the synthesis under inert atmosphere. So I performed high temperature heat treatment afterwards with more than 3 weeks annealing. And after I sintered the powder thanks to the spark plasma sintering technique, and that allowed me to measure afterward the thermoelectric properties. But before getting to the transport properties, let's get into the study of the solid solution. So I investigated several different compositions with the doping of lanthanum on the ytterbium site, okay? And as you can see here, if we add too much lanthanum on the ytterbium site, the structure is somewhat destabilized with the peaks totally slippery, showing a highly disordered structure, okay? While it is not the case for compositions below 0.3 on lanthanum. So what I did is to focus on this composition from 0.1 to 0.3 compounds and to investigate their transport properties, okay? So here are the results. These materials are quite sensitive regarding oxidation. So this is why I had to measure it in 2 times mainly. And for the mother material, all the values obtained are really higher than the previous work. So with the doped material, all the Seebeck coefficients remain on the same kind of range, and the Seebeck coefficient is not significantly improved by the doping on both sides here. While on the resistivity, you can clearly see that the resistivity is significantly higher for doped materials. Okay, and we can in particular see that the composition lanthanum 0.2 is significantly higher in terms of resistivity. And this is also in good agreement with the thermal conductivity measurement, where the thermal conductivity is significantly lower for the composition lanthanum 0.2. So basically, this is caused by the main contribution of electrons toward both electrical conductivity and thermal conductivity, where in this composition in particular, we have a lower contribution of the charged carriers. And also on the doped material, we have thermal conductivity, which is either the same or lower than the mother material, which is really interesting and proves that the phonons are scattered with the doped materials. And overall, the figure of merit of the doped material are not significantly improved in regard to the mother material, and this is caused by the high Seebeck coefficient found for the mother material, which is higher than the previous work, and actually we are not expecting such a high figure of merit for the mother material. And actually, the both doping are not improving actually that much the thermoelectric properties. And as also a side work that I performed on the thermal conductivity measurement, here is the total thermal conductivity of the mother material, and I extracted out of the resistivity measurement, thanks to the Wiedemann-Franz law, I extracted the electronic part of the thermal conductivity, displayed here in blue and brown. I took two different models regarding the Lorentz factor. I took the first constant Lorentz factor here in brown, and a model developed by Kim and co-workers in 2015, where they shown that the Lorentz factor are dependent on the Seebeck coefficient. So I implemented their model into my results, and you can clearly see that the electronic part of the thermal conductivity is way more physically acceptable, especially at high temperatures, where there is a significant decorrelation between the constant Lorentz factor and the model by Kim and co-workers. So I think it's a good behavior to use the Kim's model to estimate the Lorentz factor for thermoelectric materials. And also a second point is that, of course, the electronic part of the thermal conductivity cannot be higher than the total thermal conductivity, right? So the total conductivity was estimated thanks to the Dulong-Petit law for the estimation of the specific heat. And actually, for this material, we have an example where it does not work properly, as the Dulong-Petit law does not give an acceptable estimation of the specific heat, as it is taken as constant with temperature, which is not the case in reality. So the next work that I have to do is to perform a measurement of the specific heat for this material and get back to the total thermal conductivity to give a better estimation. So to conclude this work, overall I obtained a higher figure of merit than the previous work with the ZT of 0.6 at more than 1300 kelvins. So this is really interesting to see that we have a high performance thermoelectric material, and that can surely be improved with further doping. And the high figure of merit is caused by a high Seebeck coefficient of 100 microvolt per Kelvin at 1300 kelvins for the mother material, and this is significantly higher than the previous work that was done before. Also, I investigated the solubility limit for this family of compounds, and it was found that for composition of higher than 0.4 in lanthanum, we have a destabilization of the structure. So this is why I'm investigating only compositions below 0.3. And all the double substitutions of this family of material does not actually improve the thermoelectric properties that much. So further work has still to be done with other dopants to see if we can improve much higher the thermoelectric properties. So that's it for my presentation. I thank all the involved persons that contributed to this work. And please, if you have any question on this work, I will be really happy to answer it. So feel free to contact me. And thank you for your attention.